the basic definitions, I'll take you directly to the sketch and we'll discuss some of the part here. And this is where I wanted you to be like this is a very typical sketch of the gravity dam. Almost gravity dams are like this. If you draw the outline, and then different parts mentioned here are the full reservoir level. This is maximum water level MWL. Important thing is that dam axis is shown, and this dam axis is like this, the upstream face. This is dam's axis. You should not take it like slanting here. It should go straight, and that represents the axis. It's going down straight down here into this. So this is dam's axis. Dam's axis won't be like CG of this. No, we consider this as dam axis. Okay. This is river bed, means there was when no dam here, then what was the river flowing here, and its river bed is here, and after construction of dam, water gets filled with the with incoming inflow, and it gets filled up to full reservoir level. Full reservoir level means the water up to which we could control through the structure or through the movable structure which are gates on the spillway. So that water which is controlled is being represented by full reservoir level. Maximum water level is in case of flood. So that goes up, say above this, maybe say 10 meter or 50 meter we allow that in case of flood, it is going up max full reservoir level. This is the usual operational water operational level FRL. This remains. We intend to fill this lake, this side lake as from the water up to FRL. But in case of flood, this is a buffer provided of 10 meters, say 10%, 20% water of the total reservoir capacity. We have seen something 6,000 mm of the Sardar Sarovar. So here in this portion, maybe something like 500, 600 MCM water gets accumulated because as we go up, the volume increases. Volume of the lake increases exponentially. It is not linearly, exponentially, because the expanse, the area in which it gets spread, its own spread is tremendous. So that is why this gap here is for FRL and MWL. But for the sake of height calculation, when we say height, hydraulic height of the dam, then we must consider distance between riverbed and FRL, not MWL. So I was explaining because of this hydraulic height that we measure. This hydraulic height is lesser than the structural height. Structural height is mentioned here onto the downstream side. If you could see my arrow. Here it is mentioned the structural height. So structural height means structure, top of it from here up till the bottom. Bottom represents where? This is not the ground level or the river bed. This is river bed, and this level is below it. Maybe 10 meter or 20 meter. We scrape out this soft soil clay material and we dredge it out here. All the things been dredged out of here. And what is done? We start the concreting, dumping the concrete while constructing this from here. So up till here, up till this point, there are two layers, complete layers of 5 meter and 5 meter. If we are constructing in 5 meter layers, so till we reach to the ground level, there are 2-3 layers of the concreting. What is represented here? That this part is foundation, this part is rock, because all gravity dams the portion here represents rock, and this is this should be good. This should be good rock. If they are not good, having fissures or cracks in them, then we fill those things into grout, and then those grout height is not taken into consideration into the structural height. Mind well that we consider the structural height from where we start the concrete, dumping concrete. The base is not this much straight as seen in the sketch here. Base is not straight. This is zigzag. For the sake we provide it zigzag and to create friction. Otherwise, this structure will fail in shear. We create the shear keys to increase the shear force between this concrete and the base foundation. So the straight line is only for the representation. Otherwise, it is very zigzag, and teething is created. The zigzag pattern is created to so that it remains good in it behaves good in shear. It should not fail under the shear forces. So structural height is that this downstream written, which I have explained many times, upstream here explained many times. This the whole shape of the gravity dam is like a shoe. So this is the toe side of the shoe foot, and this is the heel side. So you could imagine your leg, your foot, and the toe and heel, and the below portion is the base width of it. This is top width, and this is the dam's axis. This one is the dam's axis. Okay. So these are the forces which are mentioned in IS code 6512. You need to refer to IS code, which has been already uploaded onto the MS Teams. Try and open sometime, browse through a certain portion of the IS code so that you could have understanding of what is there. Spend 10-15 minutes on IS code 6512. These forces, and then we'll also look at the combination of these forces for which the construction is done at various stages while planning. What are the combination load combination while early construction stage? What are the load combinations? What is the load combination for the later or when construction is almost complete? And what are the load combinations when the dam portion dam is full, the reservoir is full of water, and so those combinations are also mentioned in the IS code. And look at these. I have given different color purposefully. That first here is the weight of dam. It's a welcome gesture from the dam analysis, because more the weight, more the stability of the structure. So weight of the dam, if you increase, how you could increase? By pouring more concrete. More and more concrete if you dump, then the weight would increase and stability would increase. But that if you go more and more concrete, means it become uneconomical. So financially it won't be a viable project in that case. So we have to have a kind of optimized solution for the purpose. So this weight of the dam is calculated, and this is called stabilizing force. And the other, all these are the destabilizing forces. They also sometimes become stabilizing part of this weight. In certain cases, I will explain where and how they become. So water pressure, which water? Which is there stored in the reservoir or the upstream leg. So that water exert pressure onto the dam wall. So that water pressure need to be calculated. This is destabilizing horizontal force. Uplift force is like when water is seeping through, then it exerts the upward force. This is vertical force, and it reduces the total weight of the dam, net weight of the dam, because this is upward and weight acts downward. So uplift pressure eventually reduces the total net weight of the dam. So this makes the dam structure unstable. So uplift, the seeping water exert a force which is called the uplift pressure. The one more is the earth and silt. earth means the soil, loose soil surrounding the structure. So rarely it is important, but the silt which is there in the water, sediment and suspended silt in the water, it exerts the pressure. We need to calculate it as per the IS code. So we'll calculate, we'll find how it should be taken care. What is wave pressure? The wave pressure, the waves are getting generated when there is a wind velocity blowing, or on the surface of the lake. Lakes are like river lakes, or these reservoirs are very long, having backwater impact up to say 50, 100 kilometers, 200 kilometers in certain cases. So the backwater effect means the total net normal depth of the channel has been increased. So if there is like a wind velocity 80 kmph, 90 kmph, 100 kmph, then they will generate waves, and the wave height will come as a thrust onto the dam wall. So we have to look into that, how the wave height affect the wave structure, the dam structure, especially on the surface, and what are the measures to correct or check the effect or impact of these waves. Then
हेलो सर.
we'll, yes
सर हेलो सर, पोर प्रेशर का इफेक्ट होता है सर?
sorry,
पोर प्रेशर का,
yes,
उसका इफेक्ट होता है सर?
पोर प्रेशर का होता है, हम अपलिफ्ट पढ़ेंगे तब पढ़ेंगे। अभी मैं आगे आ रहा हूँ, जिस स्लाइड पे आऊंगा ना, I'm coming to the slide of this uplift pressure. I'll show you what it is going to be, this portion. Okay. Any other question? You may write here somewhere. So the thing is, earthquake forces, the activity, you are aware that the country is divided into 4 or 4 zones now. So all those having a kind of intensity earthquake force generating intensities, and since 2002 this has become more and more like severe consideration for design of any structure, not only hydraulic structure, but the normal these residential and commercial and skyscrapers also. We take very stringent as per codes provision, we take all precautions and include. Now all these forces which I have mentioned here are like in one way or other way are related to the water stored upfront. You look at, this is water pressure, this is also uplift is also because of water. Then earth and silt pressure, silt comes because the water runoff from the rain precipitation and flow of water, velocity of the water, it gets accumulated in the reservoir and it exerts the pressure on the wall, dam wall. Then the wave pressure is because of water stored, and earthquake forces, though we are not much into detail till point, but the earthquake forces and waves, earthquake waves, they generate the force into the water getting stored, and then they travel, and sometimes they are like adding to the stability, and sometimes they are creating the critical conditions. So all these forces in one way or other way connected to the water stored upstream into the reservoir. Then the wind pressure and wave pressure are different. Wave are generated because of the wind velocities on the surface of the reservoir water, and wind pressure is directly winds having larger velocities impacting the structure. impacting the structures, because structure is too high, say 150 meter, 200 meter, 300 meter Tehri Dam if you consider, and then if the heavy winds are blowing, then what will happen? What would be the impact of such winds on direct structure? So those pressure or the forces, uh, mostly in most of region of the country, these are not considered, ignored. Wind, though wave pressures are being calculated and taken into account, but wind pressures are mostly ignored, except these structures are built on coastal areas where wind velocities are really too high, and they are high for a quite long period of the year. Ice pressure is important in the cold countries and areas where there is a problem of ice uh, formation on the surface of the water. So you could connect here also with this ice pressure, because it's not directly ice coming into the, or snowfall getting converted into ice. It's not. See the reservoir water which is there, the top layer gets frozen, and the formation of ice means the volume expansion, and that expansion of the volume on the surface of reservoir exerting some pressure on the wall, and that too on the top of wall. So that is something horrible in case of ice pressure and the problems of ice formation in colder regions or colder countries, cold countries. Thermal loads are like on the equatorial region or the middle portion of India, the southern part. Thermal variations are very high, from 0 degree to say 50 degrees of temperature during day and night. Temperature differences are 20-30 degree almost, and they set level of thermal stresses. So looking at the intensity of change or the maximum minimum temperature difference, these should be considered, but mostly not taken into account, because they do not put thread post thread if we calculate all these forces up till this sixth. So hardly the design changes because of last three, until unless one becoming more and more prominent. Here, the point is in onto this particular slide is that out of these 9 forces, there are some forces which are directly calculable from their unit weights, like the self weight of the dam, then the weight of the water, the weight of the silt. All these we could calculate directly, but like the wave pressure, like the earthquake pressures, they can only be assumed. It's not easy for us to directly calculate from the physical property of the material or the water or something like that. So forces such as uplift, earthquake, loads, silt pressure can be calculated. There are methods mentioned. Ice pressure is also a meteorological phenomenon depending upon temperature, can only be assumed on the basis of assumption of varying degree of reliability. So where we fall that these forces, when calculate we here, these forces are okay. So calculation of these forces is okay. But the expertise required in calculation of forces is like this. This is ambiguous area while designing the dams, gravity dams particularly. So what is the statement? It is the estimating of the second category of the forces, that is special care has to be taken and reliance placed on the available data, experience and judgment. So this engineer's role come into picture here, that you take better judgments, you calculate not the approximate values, but most near perfect values. So that is what is the meaning here. The last line is very important. I again repeat, I have mentioned earlier to you that all the structures which we build like weir, barrage or dams, we do it per unit length. We do not design every section of the dam. What we do only the per unit length. So this statement you keep in mind always, that you are designing a particular section only. There could be 10 section or 50 section, different section for a given dam of 700 meter length. But we are doing the extreme one. We are calculating the maybe central one where it is having highest the structural height or hydraulic height, and also it is having the highest number of forces acting upon the structure. So, but unit length means 1 meter we calculate, and we do the calculation based on this.